Hello, here's a video on electromagnetic waves. Here's the cool little um, picture diagram of some different properties and things we use in physics and science for waves. There's the equation, different examples, different definitions. You can pause, you can do your project on any of these things here. But we look at this a little bit more detail here. Last video we were talking about waves and standing waves. We talk about when you have constructive or destructive interference here. And so you can see how if they're in conjunction, they're in sequence, you can add those waves to get bigger amplitude. If they are in opposite sequence, then they will cancel each other out, right? You can think about this with sound, music, different amplitudes, things like that. Electromagnetic waves do the same thing. Of course, the only difference is from physical and mechanical waves is that they don't have to have a medium to travel through. They actually go fastest through no medium, and they actually slow down when they go through more dense mediums. So when light leaves the sun, travels through space, that vacuum of space, it moves at 2.998 times 10 to the 8th meters per second. As it enters the Earth's atmosphere, it actually slows down a little bit. Then it goes into your eye, into the fluid of your eye. It's even more dense than the air, so it slows down even more, and you get a nice in-focus picture on the back of your retina. If you don't have an in-focus picture, then you can use lenses that have it's a piece of glass that will have even more dense than your eyeball fluid, and so it'll change the angle of the light, and then you can see things, and it'll focus that image on the back of your retina and make it in focus, so it's not out of focus. And so electromagnetic radiation, it kind of has this same kind of thing. If you shine it through a hole, right, or it can go around corners, it's called diffraction, you don't get this sharp edge shadow, right? This would be if light traveled in the form of particles alone, which it does have photons, and we do think about in particles, but it's not the only property. This would be like if you went into the shadow of a tree and it got completely dark all of a sudden. Light actually will bend around things. The reason is because it does travel in waves, and so when it goes through the hole, if you have a pinpoint, you can see these waves that will actually get. You can see these brighter spots would be the crests. Darker spots would be the valleys or the troughs. So electromagnetic radiation and light does travel in waves. How does it do this? How does it go through no medium? What it is, it's actually the motion of charged particles. And so when you have a charged particle, what actually happens is you have the creation of electromagnetic waves, transverse waves in one x angle, and you have another transverse that is the magnetic wave. So you have electric field lines that get produced, and you have the magnetic field lines, and it will actually move in. I know I have a diagram here. Sorry. Maybe I don't. I do not. Sorry. But they go in transverse waves to each other, perpendicular to each other, as they travel through space. And so they can, when something's moving, a charged particle is moving, it can actually create these waves through space. They actually slow down as they go through more dense mediums. Here's the entire spectrum. Longest side are the radio waves, very long wavelengths. Low frequency. The opposite side is the gamma rays, very high frequency, short wavelength. Here's a better diagram here. It is a spectrum, and so when we say spectrum, it doesn't go the reason I want to show you this is that it doesn't, as you notice, this has these very distinct lines from red to orange to yellow to green to blue to violet. But that's not really the case. It's more of a spectrum where it's a gradual shift from red to orange, and then from orange to yellow, and then from yellow to green, and so forth. So it's a spectrum, and that's the whole thing goes like that for the entire thing. So it's a slow transition from one thing to another. Okay. So if we look at our scale here, these are the relative sizes. These aren't things that give it off. These are the relative sizes of the waves, the lengths of the waves. And so you can see this has 10 million meters all the way here, all the way to 10 to the negative 14th meters, really 15th, negative 16th down here, really, really short wavelengths. Okay, so the longest end is radio waves. They're going through the room right now. That's why you can use your antenna to pick it up. AM radio waves. And so the wavelengths have this inverse relationship to the frequency. And so AM radio waves are in kilohertz. Okay, that's the 1,000 waves per second, or 540,000 waves to 1,650 waves per second. And then here we have FM radio waves, which go 88 to 108 megahertz. So that's how 88 million waves go by every second. And so that corresponds to the wavelength here as AM going from about 550 meters to FM being a little close to a meter in length, right? And so if we keep moving down here, you have microwaves, you have infrared waves. Human beings, actually all mammals give off, all warm-blooded animals give off wavelengths, give off radiation in the form of infrared radiation. And so that's why you can use infrared goggles to see in the dark, see people in the dark. Then you have the visible part. If you notice, it's the smallest portion, right? This is what our eyes can detect, about 700 nanometers to 400 nanometers. And that's not it's a really small part, right? This is the only thing that humans can actually detect or see. Then you have, shorter than that, you have things that start to ionize, can be harmful to living organisms. Ultraviolet light, small enough to penetrate your skin cells, can cause damage there, cause sunburns, and can cause skin cancer eventually. Then you have X-rays. These are short enough that they can go through your body. Right, and this is why you can take a picture of the inside. You can take a picture of your bones, because these X-rays go through the soft tissue, get absorbed a little bit by the harder bone tissue, and so you can take pictures of bones and things. And then you have really, really small waves, short wavelengths of gamma rays, which they'll go right through your body. But if they interact with atomic nuclei, they can cause real damage, right? Ionizing. Another thing about this relationship, because as we have to the left, we have high or long wavelengths, low frequency. This side we have very short wavelength, high frequency. Well, another thing we can have this relationship is because there's a lot of waves going by down on this end. It's a lot of energy. So if you think about a lot of waves going by, a lot of energy. Down to the radio on the opposite side, this is another relationship, this is low energy. Okay, so you can think about those things. You can do your final project on any of these different parts. You can do it on the whole thing. You can do it on emission or absorption spectra of elements or stars. You can do it on any kind of there's branches of astronomy that you can actually get degrees in. There's radio astronomy. There's microwave, infrared. In fact, there's a lot of astronomical pictures nowadays are really exciting, because what they do is they take different parts of electromagnetic spectrums. They take these photographs in these different spectrums, and they can change the color, and they put them together. It's called a composite image. And so when you look at astronomical pictures nowadays, it's a lot of composite. So it's not just what you would see with the visual eye if you were flying through space and saw this star or this galaxy. They take a picture in all these different wavelengths, and they put them together, so it looks even cooler than it would just with the naked eye, right? So that's the electromagnetic spectrum you can do on any of those waves. If you have questions, email me, and hopefully that helps. Good luck, have a nice day, and go outside and look at the stars once in a while.